Welcome to this presentation on Hyperlink's design space exploration. Hyperlinks as a whole is an integrated family of products for high-speed system design, automation, optimization, and verification. By design, we mean all the planning and analysis that you do before layout to define the rules that you want to use to place and route the board. By optimization, we mean using automated tools to improve design performance for a metric of interest. You can certainly use an interactive design capture, analysis, review loop to improve your design, but sometimes that can take too long. We'll take a look at how hyperlinks can help you improve design performance automatically. By verification, we mean post-layout analysis, or what you do once the board is routed, to determine that the design is ready to release for fabrication. The Hyperlinks products include Hyperlink Schematic Analysis, which automates parametric checks, eliminating the necessity to manually review complex schematics, Hyperlinks AMS, a powerful circuit simulator for analyzing complex analog and mixed signal designs, Hyperlinks DRC, which provides fast, rules-based design checking for PCB layouts. Hyperlinks DRC can identify layout issues in a fraction of the time that simulation requires, and screening designs with Hyperlinks DRC before investing in detailed modeling and simulation will help speed up your design cycle. Hyperlinks Advanced Solvers, which provides accurate 3D electromagnetic modeling of PCB structures and are seamlessly integrated with the Hyperlinks SI and PI tools to provide complete front and back analysis flows. And finally, Hyperlinks SI-PI. These share a common user interface. Hyperlinks SI performs signal integrity analysis of DDR interfaces, SerDes-based serial channels, and general-purpose high-speed designs. Hyperlinks PI performs DC and AC analysis of PCB power delivery networks, or PDNs. Hyperlinks assists you with many different aspects of the analysis or verification process. With either manual or automated optimization techniques within Hyperlinks, bringing a design to best meet your requirements is easier than ever. Manual optimization, such as performing swept parameter analysis, and automated optimization, like Design Space Explorer or Terminator Wizards, allow you to have control on the information reported to you. Whether you're looking to review the changes one trace width has made with a manual optimization and singular report, or taking a deeper dive to see how to best optimize a via, Hyperlinks gives you the tools to simply and effectively guide you to your best design. First things first, let's understand what we mean when we say we'll be optimizing using design space exploration. In the world of PCB design, a design space is defined as all possible options of what a design could be, feasible or infeasible, with any and every parameter option accounted for. This means all possible experiments one may run, looking at varying trace width or length or via spacing, pad sizes, and potentially millions of combinations. A feasible design space is a subset of the full design space that contains all the possible combinations of variables and parameters that meet the design requirements. Similarly, infeasible designs are those that do not meet the requirements. Design space exploration is the process of finding a combination of these parameters and values to best meet your design requirements. Essentially, it's the process of combing through the experiments and finding the best option for your needs. From this, you'll be able to pick the design points that best meet your requirements, while ensuring that you've done your due diligence in the optimization process. This comes into play with many different designs and has endless potential. If you're looking at optimizing a via in particular, you may look at varying drill size provided by your manufacturer, anti-pad sizes, stitching via parameters, and more to achieve a minimum return loss. We'll see later that this can potentially call for millions of experiments to actually find the optimal values for these swept parameters, and how design space exploration in Hyperlinks can ease that process. The end goal of an exploration of a design space is to find the optimal combination of variable values that best meet your design goals, which may include cost, density, reliability, performance, and more. We know we don't always get the best design performance on the first try. We need to continuously improve if we want to deliver the best product. A big part of that process is using different analyses to make sure we're hitting our performance metrics and requirements to the best of our ability. Generally, this means we look at our design, either from a schematic stage or after we've routed a board, and examine certain traces or segments that we think can be improved by varying the parameters and reviewing resulting responses. As analysis software has improved to allow more and more powerful simulations, we've been able to further our ideal simulation methods. Generally, we see analysis tools producing a single output or report for a chosen experiment to tell you if your design is working or not. Traditionally, we'd make one design change at a time, resimulate, and record the resulting performance. Then, as technology has advanced, we opted for swept parameter analysis, where we sweep a few variable parameters against each other and review the numeric performance values. This method works well as far as it goes, but practical limits of simulation time limit analysis to a few dozen or maybe a few hundred experiments. What happens if our design space is much larger than that? Now, what happens if you have many variables to optimize simultaneously? What if we're looking to run 6,000 plus experiments by varying 5 parameters and want to know how they influence electrical behavior of a structure? We simply can't run that many simulations, and there's no 6D plot that can plot 5 independent variables and 1 dependent variable that's going to help us understand the relationship between design variables and electrical behavior. This is where a tool like Hyperlinks DSE comes into play. Hyperlinks DSE uses advanced optimization techniques to explore design space and improve design performance. Advanced optimization provides a better way to improve a design, either prior to physical implementation or after a failed verification. The algorithm explores a full design space to avoid getting trapped in a local minima, so the whole space is observed. As more is learned about how the variables affect the results, better points are chosen to converge to a solution faster. So what exactly is Hyperlinks Design Space Explorer? Well, Hyperlinks DSE, which is what it's more commonly referred to, is the design optimization tool that integrates hyperlinks with the powerful design space exploration and optimization software, HEADS. If you're unfamiliar with HEADS, it's a general-purpose, powerful software package that automates the design space exploration process. With revolutionary search strategies available only in HEADS, you can uncover new design concepts that improve products and significantly reduces development costs. HEADS provides an environment that assists in discovering better designs faster. It tackles these challenges by automating your analysis process, leveraging your investment in computing hardware, efficiently searching for better performing solutions, and providing intuitive ways to review the design performance. Even engineers with very little design optimization experience can use HEADS to discover optimal designs in a fraction of the time it would take to perform even a handful of manual iterations. You should consider using Hyperlinks DSE when the design space is too large to be characterized by conventional means, so when you're running into thousands or even millions of experimental combinations. Or if there is a reasonable number of design variables with well-defined values and clear defined metrics that could be used to measure design performance. Measurable performance metrics are necessary, so setting responses that are critical to the optimization of a design or feature like return loss, insertion loss, or impedance responses. And finally, you need to use HEADS with a clear design goal in mind, like staying within plus or minus 10% of a target impedance, or minimizing the peak-to-peak impedance. Again, this is all based on your design optimization goals. Sherpa is the adaptive algorithm used by DSE in the Hyperlinks flow. Sherpa stands for Simultaneous Hybrid Exploration that is robust, progressive, and adaptive. It employs multiple search strategies at once and adapts to the problem as it learns about the design space. Sherpa requires significantly fewer model evaluations than other leading methods do to identify optimized designs, and it often finds a solution the first time. This efficiency can save days or even weeks of CPU time during common engineering optimization studies. Sherpa is a direct optimization algorithm in which all function evaluations are performed using the actual model as opposed to an approximate response surface model. All of the parameters within Sherpa are tuned internally, so there are no attributes to define for this method, except for the number of evaluations you wish to perform. Some of the advantages of Sherpa are finding a better solution the first time, without iterating to identify the best method or best tuning parameters for your problem. You can also perform direct optimization based on the actual model evaluations. It identifies better quality solutions for broad class of problems and performs global and local optimization at the same time. Using the multiple search strategies concurrently is more effective and efficient when searching complex design spaces. This all enables non-experts to successfully apply automated optimization the very first time. There are two ways to use Hyperlinks DSE in the Hyperlinks flow to achieve different optimization goals. You can integrate with the SerDes Compliance Check Wizard to study serial channels, or integrate with 3D Explorer to study 3D routing structures. When using the SerDes Compliance Check Wizard to analyze a SerDes channel design, we typically receive a report with information regarding I parameters, return or insertion loss, etc. But you're in charge of finding the right elements to change or adjust for the design. With the SerDes Compliance Check Wizard integrated with DSE, you're able to further investigate your channel by studying the sensitivity, reviewing robustness, and creating surrogate models of your structure that can be used for further analysis. After establishing a viable stackup using zPlanner, you can use Hyperlinks LineSim, the pre-layout analysis environment, to capture the serial channel design. Once you have components, transmission lines, and drivers and receivers set, you're able to run a SerDes compliance check using a built-in wizard to review the performance of your selected nets. When you're looking to vary some of the properties, you can use this wizard to seamlessly push the design's data into Hyperlinks DSE for a more involved analysis to better help your designs. If you've ever used the SerDes Compliance Check Wizard from Hyperlinks LineSim or BoardSim, you know that you can sweep different parameters from the Channel Sweep tab. Using this utility allows the design team to minimize risk of high-speed design errors from the start, in the schematic stage, before layout even begins. From here, typically one would run the wizard next, and the wizard would produce an informative report with the simulated results of each combination of these varying values. But exporting to Hyperlinks DSE at this step would give you the opportunity to investigate more than just the individual results. Hyperlinks DSE can be set up to aim for an optimal eye width or height, or even both together, to find the best variation of these swept parameters that you've allowed. Unlike the SerDes Compliance Check Wizard, you'll be able to select exactly which result values you're looking for in this type of simulation. Hyperlinks DSE can be used to do robustness and reliability analysis on designs, which allows you to add variability to most parameters in a design and then see how that affects the end results. Parameters such as trace width, trace length, separation, stack-up variables can all be varied and swept, just as if they were in the Compliance Check Wizard. In DSE, however, you're able to choose how you'd like to specify constraints. In a reliability run, a failure or constraint is specified, so the algorithm will return a pass or fail. In robustness simulations, no such failure is required, so you're returned with all results. When optimizing a component of your design, such as a via, you'll use Hyperlinks DSE from 3D Explorer. Hyperlinks DSE intelligently chooses the best experiments to run to get you a trend of what variables or parameters will affect which resulting performance figures. Let's take the example we discussed earlier, the optimization of a via. Let's assume that we have a serial channel with a target differential impedance of 100 ohms. There are many factors that we can change in the channel to enhance performance, such as the stack-up material or transmission line properties. But let's take a look at the via in particular. In order to create something electrically transparent, let's look at the drill size, pad size, anti-pad size, and the spacing on the vias and stitching vias. A few tools would be used in this process, starting with LineSim, the schematic tool, to establish a baseline and verify the channel margins. 2D modeling in LineSim is quick and easy, and it's calculated through the VIA visualizer. However, these are just rough electrical estimates. If we want something more accurate to view the performance of this VIA in the real world, we'll want to simulate with a 3D model. That's where Full Wave Solver comes in, to review the 3D model of the VIA. Then 3D Explorer to set up the baseline for a 3D VIA, understanding the reference point figure of merit that you'd like to see improvement from. In this case, impedance range. Here we would also set up any sweeping parameters. Then we would use Design Space Explorer to help find the optimal design by performing the automated goal-based optimization of the design's variable parameters. In the end, you can use the resulting optimization information from Hyperlinks DSE to update your LineSim schematic and get you the best results. Since 3D Explorer is used to drive Hyperlinks DSE, you may be wondering, why use Hyperlinks DSE at all if I can set up sweeps and experiments in 3D Explorer alone? Well, let's take a look at the process of running the same type of VIA optimization process in 3D Explorer versus using Hyperlinks DSE. After setting up a channel topology in LineSim, we're able to add an S parameter element in the schematic and use it to create 3D Explorer projects that will study a particular element in the design in detail. This allows us to test for different figures of merit and improve our designs. By setting design parameters or performing swept parameter analysis, we're able to create different experiments to test in order to find out our best performing options. In 3D Explorer, we can set up a differential VIA and sweep design parameters like drill size, pad size, anti-pad size, VIA spacing, and stitching VIA spacing. Setting up this information at this stage actually helps in the DSE setup, as this information is seamlessly transferred to Hyperlinks DSE, making the setup process that much easier. Once this information is passed to Hyperlinks DSE, simply click on the parameters that you've set or even add others that you'd like, and the sweep ranges will fill automatically. The next step is setting the responses and goals. In 3D Explorer, we can set the constraints and set goals based on the design specifications. In Hyperlinks DSE, we simply tag all responses which were defined in 3D Explorer. Note that they are the same as the constraints that we would have set up in 3D Explorer earlier. Once the responses are set, you can set the optimization goal and any constraints. For this example, we decided to minimize the peak-to-peak impedance, aiming to constrain impedance values. This was also the case when we set up in 3D Explorer. So far, we can see how similar 3D Explorer and Hyperlinks DSE are. We're able to set the same sweeping parameters and add the same goals. And most of the information is migrated from 3D Explorer to Hyperlinks DSE automatically. The only difference so far is that we've set an objective in Hyperlinks DSE to follow in order to get us a result that optimizes the design's behavior. Now let's see what happens if we try to run these experiments from each tool. 3D Explorer is showing over 6,000 experiments, and luckily it's letting us know that this will take a really long time before we actually start running any simulations. It could actually take us days or even weeks to run. Right here is where we see one of the biggest benefits to using Hyperlinks DSE on optimization processes like this. We have a design space of 6,075 experiments. Although we could get more information by running every single one of these, Hyperlinks DSE uses the Intelligent Sherpa methodology to analyze this design space. Essentially, this technique uses the baseline evaluation and efficiently picks the next best experiment to run. Each new experiment teaches it what parameters and variables are getting you closest to the set goals, and it can explore the design space for the next best experiment to run to get you two key pieces of information. your optimized parameter values, and more information regarding how each parameter influences the responses. You can set as many or as little number of evaluations as you'd like, and the program will run within this design space. As the simulation runs, you can review which designs are working and which are not. It will also end with exactly which design was the best. Unlike typical instances or sweep results, you can choose exactly how you want to present the data generated from Hyperlinks DSE. You can choose from various plots or table options to review the results exactly how you intend. Correlation plots allow you to easily review what correlation factor was simulated between different parameters and results. 3D relation plots compare two variables and display how they affect a result. With color guides, choosing the relative peak or summits are even easier. Influence plots gives you a quick answer to what variable made the most difference, a question which can lead to further investigation of your design, but now with the clear direction of focus. When a design space is adequately sampled, a surface can be fitted to the points to provide intermediate values for variable combinations that have not actually been solved for. These are called surrogate models. They provide extra details of the design space to expand your exploration goals. If you've run the original Hyperlinks DSE simulation with an original goal, you can use a surrogate model to zone in on manufacturing variability or deviances that you may be expecting as you go into product development. This richer, denser dataset can then be used to compare variables or determine the sensitivity of the results to the variables. Once a surrogate model exists, the data points outside of the ones used during the initial design space explorations can be calculated very quickly, avoiding a rerun of the original DSE study. The quality of the model is based on how well the data fits. If the fit is good, then any intermediate value can be solved for very quickly. This type of modeling is useful for problems that take a long time to solve, something like a 3D electromagnetic model, and have many possible parameter values. A surrogate model solved for 10 times the number of points in a quarter of the time in one example, 750 points in about 27 minutes versus the normal 10 hours it would have taken on the initial run. The results can help the designer understand what trade-offs are available and what improvements are possible. Here, a 3D symbol plot shows relationships between antipad size and pad size against a return loss. Not only is Hyperlinks Design Space Explorer powerful, it's easy to learn and use. Hyperlinks workshops get you up and running quickly by documenting complete workflows with detailed step-by-step instructions and videos. The workshops guide you through the analysis process with working examples so you can hit the ground running on your own design simulations. In this presentation, we've discussed how Hyperlinks Design Space Explorer, or Hyperlinks DSE, can help you optimize your design's performance by exploring a very large design space in a fraction of the time required with traditional methods. Not only does it save time and effort, it provides a substantially more optimized design than is possible without these advanced methods. Thanks for your time, and remember, design optimization is easier with hyperlinks.